So today's topic is in infinite series of positive terms. First we start with series of positive terms and we study some tests, comparison tests, and we apply that comparison test to solve problems. Because as I told earlier, when do you say that infinite series converges? The infinite series sigma un is u1 plus u2 plus etc. un plus so on to infinity. It converges if the sequence of partial sums. We consider sequence of partial sums. What is that? u1 plus u2 plus etc. un. We consider a sequence Sn defined by Sn. The nth term of the sequence Sn is given by this. Now it is a sequence Sn. And what are the terms of the sequence? S1, S2, S3, so on. S1 is U1, S2 is U1 plus U2, S3 is U1 plus U2 plus U3, and so on. This is the sequence. And if this sequence converges, then we say that the sequence of partial sums converges, then we say that infinite series converges. But always it is not possible to form the sequence corresponding to a given series. It is difficult to form the sequence, or it is not proper to form the sequence. In that case, we use or we take the help of Cauchy's general principle. Cauchy's general principle of convergence. This also I explained. What does Cauchy's general principle of convergence states? It states like this: if sigma un be any series, then sigma un converges if for epsilon greater than 0, if and only for epsilon greater than 0, there exists p belongs to n such that I have taken an in that theorem. Suppose sigma n is any series, then sigma n converges if and only for epsilon greater than 0 there exists p belongs to n, so that am plus 1 mod am plus 1 am plus 2 plus etc. plus an is less than epsilon for all mn greater than or equal to p. See, in this case I have not solved problem based on this, but I solve later. So in this case, what is the advantage is we need not form a sequence of partial sums. That is not required here. Directly we apply this. It is called Cauchy's general principle of convergence. It based on Cauchy sequences that you have studied in sequences. The proof based on Cauchy sequences. Up to this you have studied Cauchy's general principle of convergence. Now we start with positive term series. Positive term series. This is first case, and this positive term series important and it is easier. So we consider positive term series. We consider some practical comparison test and some 5 different tests for convergence. Then we consider negative term series. Negative term series separate test is not there because we have the absolute convergence that I explain later. First I start with this positive term series. Sigma un is said to be a positive term series. Positive term series if all the terms of sigma un are positive, only positive. If all the terms are positive, then it is called a positive term series. For example, sigma n plus 1 by n, sigma n square, sigma 1 upon n raised to p, where p is any real number, positive, negative or any integer. P is any integer, positive, negative or 0. These are examples for positive term series. Now, first thing is the positive term series either converge or diverge. It converge to finite number or it diverge. Diverge it always diverge to plus infinity. There is no question of negative terms here. Either converge to finite number or it may diverge. Only two cases, that is positive term series cannot oscillate. That is the important thing, because here why it converges or diverges, because we consider the sequence of partial sums. Sequence of partial sums. Because when do you say that the series converges? Sequence of its partial sums converges. That is the definition. Sequence of partial sums Sn. Sn consists of only positive terms. Positive terms. Therefore, Sn is the sequence of partial sum is always monotonically increasing. Monotonically increasing it is. Understand? Suppose sigma un is a series of positive terms, then the sequence Sn of partial sums is always monotonically increasing. This is because take Sn plus 1 minus Sn. When do you say that sequence is monotonically increasing? If Sn plus 1 minus Sn is greater than 0, that is Sn plus 1 is greater than Sn for all n, then we say that sequence Sn is monotonically increasing. Now this Sn plus 1 and minus Sn is, what is Sn plus 1? What is Sn here? I take un is positive term series. Sn is u1 plus u2 plus etc plus un. What is Sn plus 1? Sn plus 1 is plus 1 you have to add, that is u2 plus un plus 1. So Sn plus 1 minus Sn is, it is un plus 1 and it is greater than 0. Why un plus 1 is greater than 0? Because it is positive. All the terms of the series are positive. Therefore, or sometimes we may take Sn minus 1, but there is no problem. Sn plus 1 minus Sn is greater than 0. This implies Sn is monotonically increasing. Now what is the important thing of this? A monotonically increasing sequence converges if it is bounded above. Suppose it is not bounded above, then it diverges. Only two cases are there. Suppose this sequence is bounded above, then what happens? It is monotonically increasing, therefore it converges. Hence, this sigma un converges. Suppose it is not bounded above, then what happens? Monotonically increasing sequence, if it is not bounded above, it diverges to plus infinity. Correspondingly, this sigma un diverges to infinity. So, the first thing is, I think it is clear to you now. What is that? If sigma un is a positive term series, then there are only two chances. Either it converges or it diverges to plus infinity. A positive term series therefore either converge or diverges to plus infinity. That is the first thing. That is the first thing all of you should understand. Now I take this theorem. Theorem is a series sigma un of positive terms converge. A series sigma un of positive terms converge if and only if there exists a number k such that u1 plus u2 plus etc plus un is less than k for all n. That is what I explained now. A series of positive terms sigma un converges if there exists a positive number k so that un plus u2 plus etc it less than k. If and only if. The proof is like this. Two parts are there. Suppose u1 plus u2 plus etc plus un is less than k for all n. This implies Sn is less than k. Because what is Sn? Sn is sequence of partial sums where nth term of the sequence is given by Sn is u1 plus u2 plus etc un. It is less than k. This implies the sequence of partial sums sequence of partial sums Sn is bounded above. Therefore, the series is bounded above. Series is bounded above. And also, Sn is therefore monotonically increasing, bounded above. Therefore, it converges. That is the first part. What is the theorem? A series sigma un of positive term converge if and only if there exists a number k such that u1 plus u2 plus un is less than k. Now we have taken u1 plus u2 plus un is less than k. This implies Sn is less than k because Sn is given by this. In the case of sequence of partial sums Sn is defined by this. Sn is less than k. This implies sequence of partial sums is bounded above. Since Sn is monotonically increasing and bounded above, it converges. Second part. On the other hand, what is the second part? Second part is if the series is positive term series is converges or is convergent, then u1 plus u2 plus un is less than k for all n. That is the converse. Suppose sigma un is convergent. When do you say that sigma un is convergent? By definition of infinite series. When do you say that sigma un is convergent? Then the sequence Sn of partial sums is convergent. Now every convergent sequence is bounded. See where I have taken from this result? I have taken this result from sequences. Very beginning of the sequences you have studied all these things. Say I explain here. Converse. What is the converse? Suppose sigma un is positive term series, it is convergent. What you have to prove? u1 plus u2 plus un is less than k. For that, if the series sigma un is convergent, then the sequence Sn of partial sums is convergent. But every convergent sequence is bounded. Therefore, what happens? Convergent sequence is bounded. Therefore, Sn is bounded above. This implies, when do you say that sequence is bounded? That also you have studied in sequences. This implies Sn is less than k for all n. Then you say that the sequence is bounded above. This implies what is Sn? u1 plus u2 plus etc plus un is less than k for all n. These things seems to be very simple, but they play very important role throughout the further study of infinite series. So, what is the theorem? A positive term series sigma un is convergent if and only u1 plus u2 plus un is less than k for all n. I think the proof is clear. You go through again. Second, next theorem. A series of positive terms sigma un diverges to infinity if and only if the sequence Sn of partial sums is unbounded above. Proof is exactly similar to this, and you try that one. Now come to the important topic. We take this as a theorem, or it is comparison test 1. Say here the actual topic of infinite series begins here. Actual topic means the interesting topic begins here. Comparison test 1. Say what does this test says? We take this as theorem. If sigma an and sigma bn are two positive term series such that an less than or equal to bn for all n greater than k. Suppose there exists a positive integer natural number k, so that an less than or equal to bn for all n greater than k, and sigma bn is convergent, then sigma an is also convergent. Very important theorem it is. First one, if a and bn are two positive term series, here I have used an and bn. Usually series are denoted by un. I have taken an and bn because two series are there. So that an less than or equal to bn for all n greater than k, then if sigma bn is convergent, then sigma an is also convergent. Next theorem is an less than or equal to bn for all n greater than k, and sigma an is divergent, then sigma bn is divergent. Carefully understand these two theorems, and you have to get mastery over these two theorems, because throughout the study of infinite series we use this theorem. What is that theorem? Sigma an and sigma bn are two positive term series such that an less than or equal to bn for all n greater than k. Then if sigma bn is convergent, sigma an is convergent. Say upper one, sigma bn is greater than or equal to an, and sigma bn is convergent, then sigma an is convergent. Suppose sigma an is divergent, then sigma bn is divergent. In case of divergence, the less than we take, sigma an diverges, then sigma bn diverges. But first theorem is if sigma bn is convergent, then sigma an is also convergent. Now proof also important here from examination of point of view. Proof also important. I explain how to prove this one. Again, proof based on definition of convergence. When do you say that a series converges? If sequence of partial sums converges. So we take sequence of partial sums. Let Sn and Tn be the sequence of partial sums of partial sums of an and bn, sigma an and sigma bn, first step, respectively. Then I take Sn is equal to sequence of partial sums of sigma an. It is Sn is a1 plus a2 plus etc plus an, correct? An. Now it is a1 plus a2 plus etc plus ak plus 1, because k is less than n, ak plus 1, so on an. It is equal to, say, up to ak, what is given? An less than or equal to bn for all n greater than k. So we write this as sk less than or equal to, now I write a1 plus a2 up to ak is, we have no idea whether a1 is less than or equal to b1, we don't have any idea. We have only for all n greater than k, an less than or equal to bn. So we use ak up to ak as sk by our notation, plus less than sign or equal to sign here, because ak plus 1 is less than or equal to bk plus 1, ak plus 2 is less than or equal to bk plus 2, an is less than or equal to bn. So it is equal to sk plus, now I write this as, say, what is this? Tn, it is a sequence of partial sums of series bn. So it is Tn minus Tk. This step important. I think all of you followed this, because what is Tn? Tn is A1, B1 plus B2 plus etc. plus Bk plus so on plus Bn. Now Bk plus 1 etc. Bn is Tn. B1 plus B2 etc. up to Bk is Tk. Therefore Sn is Sk plus Tn minus Tk, less than or equal to, it is less than or equal to. Therefore Sn is less than or equal to Sk minus Tk plus Tn, that is equal to C plus Tn for all n it is now, for all n, because we have taken this as C. Now what is this? It is a constant. What does this imply? Sn less than or equal to C plus Tn for all n, for all n. Now see, the next step is, what is given? Sigma Bn is convergent. Sigma Bn is convergent. Therefore Tn is bounded above. Tn is bounded above. Because it is a positive term series. See the previous theorem. After a positive term series, we have proved one theorem. What is that? A positive term series sigma un is convergent if and only if the sequence of partial sums Sn is bounded above. I have proved that one. That is u1 plus u2 plus un is less than k. That theorem. Now Tn is bounded above. From 1, I take this as 1. From 1, Sn is also bounded above. Bounded above. This implies Sn is convergent. Sequence of partial sums of sigma an is also convergent, because Sn is bounded above. Why it is convergent? Because it is monotonically increasing. Monotonically increasing. Positive term series, the sequence of partial sums is monotonically increasing. Therefore Sn is convergent. This implies sigma an is convergent. Is convergent. See, very important result it is. What is the theorem says? Theorem states like this: if sigma an, sigma bn are two positive term series and an less than or equal to bn for all n greater than k, then if sigma bn is convergent, sigma an is also convergent. This is the proof. We go through the proof again. Simple it is. Only definition of that convergent series is used. Second, if sigma an, sigma bn are two positive term series, and an is greater than or equal to bn for all n greater than k. Now we have taken an greater than or equal to bn, and sigma bn is divergent. Sigma bn is divergent, then sigma an is also divergent. Very basic results there in infinite series. First theorem was an less than or equal to bn and an convergent, then bn also convergent. Or an less than or equal to bn convergent, an convergent. Now an greater than or equal to bn for all n greater than k, and sigma bn is divergent, then an also divergent. Understand this? Proof is again like previous one. Proof of this. First we take Sn and Tn be sequence of partial sums of sigma an, sigma bn. Sequence of partial sums of sigma an and sigma bn. What is given? It is given Sn is therefore, what is Sn? Sn is a1 plus a2 plus etc. plus ak plus 1 plus etc. plus an. Now it is equal to sk. I write greater than or equal to, because an greater than or equal to bn for all n greater than k. Therefore from this ak plus 1 onwards we can take it is greater than bk plus 1. ak plus 1 onwards we can take ak plus 1 is greater than bk plus 1. So we keep this as sk itself up to ak greater than plus bk plus 1 plus etc plus bk. Therefore it is sk plus, what is this now? As in the previous theorem, it is tn minus tk. Tn minus tk. Correct? Tn minus tk. You know the meaning of Tn minus Tk because Tn is clearly defined here. Therefore, it is Sk minus Tk plus Tn. Tn. That is C plus Tm. Take this as 1. Therefore, Sn is greater than or equal to Sn is greater than or equal to C plus Tn for all n now, because C is independent of n now. C is independent of n. It is constant. So Sn is greater than or equal to Tn for all n. Now what is given? Sigma Bn is divergent. Therefore, the sequence of partial sum Tn is unbounded. Is unbounded. Unbounded. From 1, the sequence of partial sums of that an Sn is also unbounded. Also unbounded. Now see go to the very preliminary in the positive term series. What is that? A positive term series either convergent or divergent. When it is convergent, if u1 plus u2 plus uk is less than k, that is bounded. Otherwise it is divergent. Now what happened here? This see come to this last step. From 1, the sequence of partial sums of that an, sigma an is unbounded because of this. Because of this. Therefore, Sn is divergent. What is Sn? Sequence of partial sums of an is divergent. This implies sigma an is divergent. Is divergent. So these two theorems are very fundamental. Proofs are also important. I think you followed the proof of this one. So in case of this infinite series, sequence also concept very important. Sequences. Say what we have proved here. If a and bn are two positive term series and an greater than or equal to bn for all n greater than k, and sigma bn is divergent, then sigma an is also divergent. See this one, an is greater than or equal to bn here, sigma bn is divergent, so sigma an is also divergent. How we have proved this one? We have used the definition of infinite series. When infinite series diverges, if the sequence of partial sums is divergent. Now we have formed a sequence of partial sums for these two. Sn is, we have proved that Sn is greater than or equal to Tn, C plus Tn. Therefore Sn is, since Tn is unbounded, Sn also unbounded. Therefore Sn, sequence of partial sums of an, divergent. Therefore sigma an is also divergent. Now go through these two theorems, they are very important. We use these theorems to solve many problems on infinite series. Now in the next period, I consider practical comparison test. Okay, thank you.